Okay, so today we'll do PAC Learning, which is sort of a learning theory topic, but it's gonna, I'm gonna try to argue that with our randomization background, actually, it'll be not so hard for us to absorb this. And I also just kind of like the idea of, you know, touching on a diverse set of topics, right, and kind of making lots of connections across different things. This will have very strong connections to what we did last time, which felt like a geometry and sampling lecture. And here we're talking about learning. So that attitude I like very much. So uh, so last time, what did we do last time? So last time we did epsilon nets, epsilon samples, least dimension kind of stuff. We used the additive turn-off bound for the first time because we were kind of in this normalized regime between 0 and 1. Finally, additive sort of made sense there. So again, epsilon sample was in this setup where you have these points and these ranges, and you have this measure kind of what fraction of the points is in a particular shape. Epsilon sample means you want to make sure you hit every single kind of substantial shape, every shape that has mass at least an epsilon fraction. And then I'm sorry, that's an epsilon net. Epsilon sample is when you want to get enough points so that when you look at, that subset of points kind of estimates the proportion of points it contains, and you want that to be within an additive epsilon. Okay, so those were the two different things. And we were characterizing most directly ranges by their growth rate. If you have n points, how many kind of interesting, essentially distinct shapes are there? So with n points, it was n cubed circles in the plane, because each circle is kind of wraps tightly around 3 points that characterize it, and so on and so forth. So what we showed is that you can start getting epsilon samples of size depending on the exponent of the growth rate. So if you get polynomial growth rate n to the d, you only need like d points in your sample to start getting interesting estimates. Okay, and if you're doing an epsilon net, you're just trying to hit all the kind of heavy shapes. It goes down from epsilon squared to epsilon. But the key point is that the number is now completely independent of the number of underlying points. Okay, it's just a function of the complexity of the shapes. And we'll see that being kind of a very nice fit with learning theory today. Okay, so right, so maybe how many of you have taken a learning theory kind of course? So maybe okay, so not too many of you. So for most of you, these will be new definitions. We won't go off the deep end, just the basics, but actually pretty foundational basics. Um, and yeah. So okay, let's just get started. Uh, this actually happens every year. Uh, I always intended to make up an example, and then every year I forget, and we just get this awkward blank slide. So anyway, okay. So consistency. Okay, so the high level goal is to somehow come up with some model. We have some kind of notion of learning, like you learn as you grow and you maybe learn in this class or something, right? And we want to try to model it, right? So, rewind 50 years ago as early computer scientists, theoreticians, trying to come up with some kind of model for learning, some algorithmic computational model. Try to think like Turing or something. He was interested in this. Okay. So the first one, basic one, is called the consistency model. So let me explain, let me introduce the points. Actually, does anyone want to guess like what are some ingredients for a model? What should a learning model have? What does it mean to learn? No wrong answers, although I guess there is a right answer for this particular slide, but yeah. Okay, sure, maybe optimize something. Okay, so optimization maybe as a word, some quantity. Huh? Tunable parameters. Sure. Uh, yeah. Have a way to. Oh, okay. Unseen. Okay, so now you're also dividing between seen and unseen data. Okay, those are also important considerations. Any other high-level ideas? Yeah, getting better with experience. How can we even define experience, or what form does experience take? Sorry, conditional probability. Okay. So what does something look like? So I think one of these tenets is just some kind of space of examples. Yeah, and labels. So we're going to be doing some kind of classified learning. You just see something. Is it a dog? Is it a cat? Is it a fish? And so in the consistency model, you're going to assume there's some underlying set of concepts. So these are functions that assign labels to examples, and from some fixed class. Okay, so you could study like, oh, any possible labeling, or you can restrict it. Okay, certain labelings, I'll give some examples in a moment, somewhat limited. Okay, and so what you do in this consistency model, we'll talk about maybe shortcomings in a moment, but in this model, you assume that X, uh, which you could think of as a finite set or maybe even distribution, but let's say it's finite, is labeled by some concept, but you don't know it. Okay, so there's some finite class, okay, and you don't know it, and the high level goal is to take a limited amount of data, so just points xi from x. Maybe if x is finite, it's just uniformly random. Maybe it's coming from a distribution. And you get the labels for these, the true labels. And the question is, can you identify C? Or sometimes they'll ask, how much data do you need to start identifying D, C, and things like this? Yeah. That's the high level goal. That's not very quantified yet. Okay. So given trainings, labeled data, labeled by some concept, and you have some other concept C prime. Okay. We're going to say it's consistent if it agrees with all the labels. Okay. So, interesting. So a learning algorithm in this consistency model is either going to output a consistent concept or declare that no such concept exists. So this is really like a search problems through a space of concepts. You have some data and you want a concept that fits. It's depending on the concept class, it's almost like a data structure or retrieval-ish looking problem, geometry problem. Okay, so let me give some examples to make it concrete. Okay, so um, suppose we're looking at disjunctions. Okay, so a single piece of data, let's say here we have 5, has 5 binary features, 5 Boolean things. Okay, and there's some unknown disjunction, A or B or not C. Okay, that gives the label. Okay, and so that's the concept class. Your promise that these labels are coming from some unknown concept. Okay, but it has to be a disjunction that you're promised. The question is, can you find a good disjunction? One that works for the labeled data. Like take even this example. What would be a disjunction that works? Here, x1, x2, x3, x4, x5. X what? X, what's XR? What's R? Oh, well, express it as a disjunction for me. We're only allowed to use disjunctions. Oh, Adrian thinks one does not exist. Yeah, there's nothing in the yellow square. Anyone come up with a disjunction that works? Yeah, not x2 or not x what? x5? Okay, does that work? Yeah, it seems to be consistent. Okay, survey says. Oh, okay, that's okay. So that would be an example of a disjunction that agrees with the label data. Okay. All right, so how would you do this systematically? Let's come up with an algorithm. You can do it on a 5 by 5 example. How do we do this in general?
You set up like a 3 set to solve it.
You're going to set up a 3-set to find the disjunction.
Maybe.
Okay, well, let's try to get a fast algorithm because 3-set is like pretty tough. Okay, I'm claiming there is a an algorithm. Yeah. Oh,
I guess you can start from first variable, like go from x1 next to xn.
uh-huh.
You would have the process that for everything x, you would have like zero length, like that's for zero. And then based on these two classes, you see you can like make consistent either x1 numbers or x1. You can't find consistent one, then you just discard it. So it's like
Okay, I think I know what you're saying. So let's just go through one example slowly. So let you start with x. You're going to loop through the variables, right? And you said, okay, I'm going to look at x1 first. Now, I look at x1 and I look at all the samples, and what should I do?
and then maybe you had the red ones first, so these are like
Okay, so we'll look at all the false ones.
so we have 0, 1, 1. But 0, 1, 1, so x1 can be true, it can also be false. But since we have both and they're all false, that means that x1 does not matter in that case. So,
Okay, so we're looking at the first column, and for false, we have both x1 is 0 and x1 is 1. So we probably can't include x1 or x1 bar in our formula because that would improperly label something as true. Okay. And then you can imagine redoing this for all of the variables. Okay. So this is like some kind of greedy algorithm. We're basically trying to add any disjunction we can. Yeah. Okay, so that's I think that's basically should be consistent with what I wrote there in some contrapositive form. Okay. All right, so good. So that means if you apply this algorithm to that example, I think you might get something a little bit different. You'll get not Z2. You also find not Z4 because both of the not Z4s uh, come out to be, no, that's not right. Or Z4. Yeah, this algorithm would actually try to take Z4. Okay? Which maybe is kind of counterintuitive because somehow, I mean, it doesn't seem that natural because Z4 is always 0, but this algorithm is greedy. It'll try to kind of give the biggest disjunction. Okay. So, so this claim we've already kind of done implicitly. Since this is adding every agreeing variable, whatever is a true concept is going to be some subset of our disjunction, so to speak, some sub disjunction. Okay. Good. So, oh, nothing down there. Okay. So anyway, we get a consistent learning algorithm. Okay. All right. So good. Just that you're able to output some disjunction that works, and you're able to do it fairly efficiently. Okay. It's not a huge thing. Okay. All right. So now maybe a different example is your data points. The examples are points in the plane, and your labels are red or blue or something in this example. And the class of concept is rectangles. Anything induced by a rectangle. Okay. So the question to you is to design a consistent learning algorithm in this setup.
So can only be one rectangle?
Well, you're promised there's some unknown true rectangle. Yeah.
Just find the highest point, the leftmost point, the rightmost point, the lowest point.
Okay, so we find the highest point,
And Like there's no points inside of it.
Well, if you're promised that it's actually labeled by a true rectangle, then you're guaranteed that you won't get any of these kind of contradictions. Yes, okay, so this is trying to find the tightest fitting square by just getting your leftmost point, your rightmost point, upper, lower. Okay. So the rectangle you would output in this algorithm would be this inner one. I guess I could do that better. Okay, something like this. Okay, any other algorithms that would work?
Kind of the same thing, but like you start at a random point and then you go through like every single point. So gradually.
Oh, okay, so that would still output the smallest rectangle. Any other? Yeah.
Just at the protocol.
Yeah, you can do kind of the dual kind of one, where you figure out you could try to output the biggest rectangle. Like this.
Okay, but how do you do that?
Good question. I guess there's different ways to do that. I don't know if it's actually biggest. You can output,
Also,
oh yeah, I guess that's one thing you can do is that there's only so many interesting rectangles in the blue. Yeah, so you can iterate through all of them because they have to be kind of constrained by the blue, right? Okay, good. All right, so right, so you can output the smallest and largest rectangle containing, exactly the positive labeled points, right? And anything in between is also valid. You can output their average or something. Okay, so right now, all right. So what is, maybe one thing that this model does not stress are the points you don't see, right? So, at some level, you're probably interested in taking the thing you learned and then applying it to some new points. So you're kind of interested in doing relatively well on these kind of dotted points that you haven't seen yet. Yeah. So at some level, this model, I think this word has already come up, does not put any emphasis on like generalizing. Okay. So are we really learning? So this is a very natural model. These are early days of computing. It's like an algorithmic problem. You can imagine going through all sorts of shapes and coming up with faster algorithms and clever algorithms and this and that, right? Dynamic algorithms, whatever you want. But as far as the model goes, you just have to output some concept class that matches. But it doesn't really care about the true concept class. It just has to fit the data, and that could lead to overfitting or kind of counterintuitive or things like this. Okay, so that brings into this next model. The weaknesses of consistency learning motivate the next one. It's called probabilistically approximately correct learning, and was proposed by Paul's dad, Leslie Valiant, 1984. Okay. So, okay, so what are the ingredients? The initial stuff we'll inherit everything from consistency model, and then we're going to start adding stuff. So, what are we going to add? Let's see. Okay. So we also have a family of hypotheses. So one thing we're going to do is we're going to allow like one family of things that are truly labeling it and one family of things that we're guessing. And it's possible they're the same. H could be equal to C, but this model allows for slightly more general things where C can be different from H. And I guess the next ingredient is we're always going to assume that the points are drawn from some fixed but unknown distribution. So maybe you can ask for a new point from the set, but you don't really know the full distribution. Yeah. And okay. And so any hypothesis has like a true classification error based on if I draw a point from the distribution, what are the odds that my hypothesis gets the same label as the concept? Okay, so there's already some kind of notion of error. The consistency model was all or nothing, right? But we already have this kind of fractional values in between. And the high level goal is kind of to find a hypothesis that minimizes the true error. Okay? The true error. The true error is somewhat idealized because it's, if you could take an infinite number of draws from this distribution and stuff. Okay, good. So that's the high level idea. Now to make it a little bit more concrete. So, okay, so PAC learning, probabilistic approximately correct. So this is like a definition for like what counts as a learning algorithm. It needs to satisfy this to be satisfactory under this model. Okay, and you could think of it as like a relaxation to some extent of what we just did. So first you're going to draw some points from the distribution. Okay, so you have some particular error. Maybe it's actually better to do the output part first. So you have an epsilon parameter and delta parameter, and maybe this is a really key point. You want to make sure that with probability at least 1 minus delta, you're going to output a hypothesis with true error less than or equal to epsilon. Now, this latter part definitely makes sense. Okay, I want to output something with true error. But why should I even start allowing for something like this? Because I could have omitted this out, right? I said just output something with error h less than or equal to epsilon. So what might motivate this you should output a good hypothesis most of the time? Yeah. Well, generalization, sure, or some level. This is almost a definition of generalization, but how more concretely? Yeah.
Set might not be very good.
Yeah. So some level, as soon as my input's coming from a distribution, there is whatever the distribution is, there may be a minuscule chance that you get a completely non-representative data, right? So this 1 minus delta, if nothing else, allows for bad draw of data. Okay? Your algorithm may also be randomized or have other sources of error, but at the very least, this gives some possibility of the input just being bad. Okay, which is sort of reasonable as soon as you tag this distributional input. Right? It seems kind of simple. This is important though when you're setting up a good, robust model that stands the test of time. And the other point of emphasis, what might be the other point of emphasis? Well, I guess it's hidden in a box, but yeah. So in principle, what you really want is you want a model that doesn't need too much data to learn. Okay, and it would be very nice to get something that's really just a function of 1 over epsilon and 1 over delta. Like everything we do will be log of 1 over delta, but you want just like, okay, if you want smaller error, give me more data, but some bounded limited growth. Yeah. So the true error of h is a true error. What are the odds of it getting the right label when x is drawn from a distribution? But of course, you can't really compute this, right? You only have a limited access, right? That's what makes it interesting. Assuming you only have a small number of samples, can you still, with reasonable probability, output something with truly small error? Okay, but there needs to be some tension. If you want smaller epsilon, then I should be allowed some more samples. Okay. Yeah.
So the hypothesis class is like where the data come from, like hypothesis class. I accepted that.
No. Yeah. So it's good to get this right. So, okay. So maybe we'll start here. Okay, go back here. So originally the consistency model. Okay. So the data is coming from some fixed but unknown distribution D. Okay. And you're promised that the data is labeled by an unknown concept. So there's some family of labelers. They could be rectangles, they could be more complex. Okay. You don't know which rectangle is labeling it, but you're promised there is a rectangle. And you're promised the points are drawn from a fixed but unknown distribution. Okay. The hypothesis class is what you're allowed to output for your classifier. It could just be rectangles. Your algorithm's expecting a rectangle and outputs rectangular classifiers. But this model allows the hypothesis class to potentially be different. Okay, but for simplicity, even when the case where h is equal to c is already interesting and maybe captures most of the nuances of the model. So the distribution is kind of separate from the concept is labeling the x's, and H is your family of guesses. It may be natural to think of H as always equal to C, but we can allow for some difference. Yeah.
You mean like about how big H and C are?
Yeah, so the problem will vary depending on what concept class and what H you're looking at. So we haven't opened that up yet. But yeah.
But how we
No, you're not promised that C is from the family of hypotheses.
like some like closest members in the family of hypothesis that is close to C, like senior that there is.
That's right. That's right. And we'll often get like, I think our results will often have the form of like, if there is a hypothesis with small error, we can do this. Or if there is a consistent hypothesis, then we can do, yeah. So I think all of our positive results will kind of be as if you're promised there's something good. Yeah. It'd be a little, yeah.
How many concept C has to be like, do we always know that it's like a family of triangles or not?
Well, I guess like here we should maybe distinguish reality and theory. So but they want to set up the theory problems that says, okay, if you have some distribution in this particular concept class, will we be able to learn that concept class with this hypothesis class? Now, in real life, the data and labels are not coming from a particular concept class, but it is still kind of capturing the idea where like, well, you know, real life isn't completely arbitrary. You know, it's still coming from a reasonable subset of ways things can happen, whether it's Darwin or whatever, you know, other biological theory or something, right? So you're still hoping that real life is governed by some small subset of all possibilities, compact subset. And then can you kind of capture it? But yeah. Okay, yeah.
Take an example, you would want to pick a hypothesis that's like in the middle of the smallest and largest because we
Yeah, so now okay, just going back to here. Uh yeah, when you have something like this, yeah, it might want to start motivating choosing something in between, right? Maybe. Although it could vary on the distribution. The distribution could be very nasty in certain ways. But also when it comes to rectangles, there's sort of an interesting question of, see, we're not, so the point of emphasis will shift a little bit. It won't just be about selecting a hypothesis. So it is true that with the consistency model, all the emphasis was on choosing a rectangle, right? But here the emphasis is also going to be on how many samples do I need so that I start feeling good about the rectangle. So a slightly different way to pose this question is like, suppose you're committed to a particular algorithm like smallest rectangle. How many data points do I need to start feeling good about the small rectangle? A question.
with the what the poly function means.
Oh, any polynomial.
Okay.
Yeah. So Leslie Valiant said, it's not interesting if it's exponential and 1 over epsilon.
So it takes both 1 over delta as 1 over spread.
Yeah, I mean, it's really just, we're going to see how many labels we need to, basically, we're going to try to figure out how many data labels we need to get small error, assuming it's possible. And then hopefully we want this to be basically as small as possible. In general, we want this to be small, right? Because you want less data to learn your thing. That sounds just like running time. We want the amount of data we need to be small because it's a resource. And then Valiant defined PAC learning as something that's efficient both in computation. Actually, I don't know if computation was a point of emphasis, but definitely efficient in terms of data. And I think kind of inspired a bit by, P versus NP, he defined efficient in terms of data as polynomial and 1 over epsilon 1 over delta. It's a little bit arbitrary, but clearly it's naturally inspired by the usual polynomials good, exponentials bad kind of spirit of computer science. Yeah. Got my standing goal. Okay. Any other questions? Yeah.
Are you saying that the military report, the amount of data that you solely depends on like probability that like or like an error error let me have, and it does not in fact and the number of data we have. Like shouldn't be the amount of data was
Okay. So I think once you take the distributional point of view, then you're not really in this kind of fraction mindset. You know, the phrase fraction of all the points doesn't make quite as much sense from the perspective of you have a distribution of points. So I have an infinite amount of points, but they're coming from different probabilities. So I think that's yeah, slightly different kind of perspective. Yeah.
It's also I know that the concepts are from the concept class. I actually don't know what the concept is for. But if the concept class is a subset of my hypothesis space, would I just always look for the concept class? Or maybe some case where I
So even here when H is equal to C, right?
see it's like the rectangles.
Yeah, H could be anything. But if you knew C was rectangles, then you might come up with an algorithm like, oh, let me output the smallest rectangle. And that always be consistent with the data. But it doesn't say anything about generalization, which is sort of what you know, the out of training data, right? So what this definition is really doing is saying, look, it's great that your output is consistent with the data. That's not bad. But does it have true good error? You've only seen some arbitrary subset of the data, or it's, I mean, drawn independently from distributions, so not totally arbitrary, but you've seen a subset of the data. And to what extent, you know, the shrink wrapping, the sample of data, give you something that has small error in general, right? Because you don't want something that's like, because obviously if you just got like 1 point, you just output some tiny rectangle around 1 point, right? And that wouldn't generalize much at all.
Yeah, I'm looking at the concept class and I'm guaranteed to get 100% no error basically. But the con is that it might take me longer to restrict myself to that rather than generalize I might be able to do something with a little bit of error, but it's might be through once to generate. That makes sense.
Yeah, I mean, if you have a bigger H, you have more degrees of freedom. So it's only going to help you. But at some level, there's some trade-offs. But okay. So remember, we haven't done any algorithms yet. This is just a model where he's just trying to say, hey, this is maybe a notion of learning that and sets up a game that we can play with. And it's probably doesn't exactly match what you think of learning, but there's some tensions here between getting true error and worrying about how many samples you need, right? That's some of the tensions involved when you think of learning. Yeah.
H that's not fully consistent.
You're allowed to pick an H that's not consistent. Yeah. H may be a subset of the consistency class and things. All he's really doing is you're just separating the two. They don't have to be the same.
Is the error defined to be the maximum of the profit with just X with this?
X is drawn from D. So this is the expected value, you know. So this is like if you had done the experiment infinite number of times and it outputted the score. Yeah. Okay. I mean, yeah, and certainly, yeah. Does this have anything to do with LLMs? That's you know, learning and the definition of learning has kind of radically changed in the last, or you know, the popular notion of learning has radically changed in the last 5 years. Now that you can talk to these things, but anyhow, right? But this is, you know, a theoretical framework. Okay, I think it's served its purpose too. It's sort of you know, once you set this up, you set up a game kind of that people can, you know, it helps people focus on something, right? Once it gets kind of specific and concrete, you set the rules, and there's so much that followed, you know, in this whole learning theory. We have several professors who do, you know, hardcore learning theory, right? So it's a real field now. Okay, good. So let's say the distribution was uniform, okay, over some space in this 0, 1 square, okay? Then as you sample more and more points, right, you're hoping that it'll take you, you know, closer and closer to the true concept class, right? So as you get more points, in this particular example, your thing is getting better and better. right? Because that now has to be small enough to fit and things like this, right? So you're expecting things to get better and better. The smallest and largest rectangles are going to converge, right? But there's some, mathematical question of at what rate it converges and stuff, right? And you can just directly analyze, after I've gotten 100 points and I output the tightest rectangle, what is my expected error of the shrink? And you have all the data you need to do some calculations. Right? It's a math question. Okay, good. So, all right, now, okay, so here's our first kind of not too difficult theorem um, in this framework. So suppose that the number of hypotheses was finite. Okay, some constant. Okay. Question is how many okay, so now let's look at this theorem. It says if m is at least something or something you'll guess, okay, there was probably at least 1 minus delta for a finite hypothesis class. Every consistent hypothesis has error at most epsilon. I mean, that's kind of appealing, right? Because if you have a consistent learner, okay, and you've taken enough samples, then you're going to get something with good true error. And if you can find a consistent hypothesis. Okay. All right. In fact, I think that's probably down here, right? So any case that where you had consistent learning, like we did like the rectangles, right, implies PAC learning for some fixed and finite h. Okay. All right, so anyone want to guess what this should be?
Well, how many over epsilon squared?
Yeah, if by W you mean the cursive H, so something like this: log H over delta over epsilon. Did you say epsilon squared or epsilon? Okay, epsilon. Good. I guess we'll prove it in a moment. Okay. Now, who wants to try to prove? So this says, okay, if I take as at least that much data, okay, then anything consistent with that data should have small true error. Okay, so why? The 1 epsilon instead of epsilon squared is sort of a hint. No, actually, we won't use additive turnoff because that's going to require an epsilon squared.
You just should
So yeah, let's propose. So a little more the true error.
being sample distribution, like having the wrong classification.
Yeah. So what does our algorithm want to avoid outputting? Yeah, so let's say that H is bad if error H is at least epsilon. Right? And there's at most size of H, size of W, bad hypothesis, right? Because they're all okay. So I want to make sure that I don't output a bad hypothesis. How do I make sure the consistent learner doesn't output a bad hypothesis? Yeah, so you want to make sure it doesn't agree with all the samples, right? So you want to make sure you sample, in particular, a mistake. Because sample something that makes a mistake, yeah, This is like why I have to put some hard problems on the exam, right? So that okay. Uh, good. So okay. So you want to make sure that H gets a mistake. So if I drew a random sample, what are the odds that it'll be a mistake? Just one data point? Epsilon. So it's probably epsilon of it being a mistake. So if I do like k samples, right? And the probability that H is correct for all samples, this is assuming it's bad. What is this? We want this to be small, right? Less than equal something.
It's epsilon to the k.
1 minus epsilon to the k. Okay. And now what do we make k? Or we make k equal to, m in that bound. Why? So if we plug that in, you're going to get, okay, so this is going to go e to negative epsilon k. And then from there, you're going to get, delta over total number of hypotheses. Okay. Why? Now you can union bound over all the bad hypotheses, which is at most the total number of hypotheses. And you get probability delta of outputting something bad. Yeah. 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 If I outputted k samples, yeah. I probably should have used m all along. Because H is bad if its true error is at least epsilon. Yeah, so this is like a 50% student, it gets 50% of questions right or something. I want to make sure it gets something wrong. Yeah. Yeah, so if I plug in log of H over delta over epsilon, if I plug in the top bound for K, log M is greater than equal to log of, yeah, it's a little confusing because naturally I changed letters. If I plug in that, then the epsilon will cancel out. And then you have this log of size of H over delta. Yeah, M is same. Yeah, so yeah, now we union bound over H. Okay. All right. But this is not too complicated, right? We're just trying to make sure, consistent learners actually pretty good if we can make sure we hit all the bad hypotheses.
So does that mean that like how bad the problem is controlled by like how many fractions each are within the boundary?
Yeah. So we have an algorithm that's just going to output some kind of hypothesis that does perfect on your data, right? And I want to make sure that this thing that does well on this small test is good in general. So I'm just going to make sure I have enough questions on the test that if it were bad, it's definitely going to make at least one mistake.
Where's this coming from? That we need is that.
Oh, so you don't want to output anything with error greater than epsilon. Right? So it's sort of the contrapositive of our claim. Our claim is that anything we output will have small error. So that's the same as saying we will never output something with big error. Or not output with good probability. So now we're saying, okay, let's get all the bad ones with error at least epsilon and make sure we kill them by trying to sample one thing it makes a mistake on. Say epsilon is 10%. So I don't want to output anything that gets more than 10% wrong. But if I draw 10 points, then something that gets something 10% wrong should expect to get one wrong. If I start drawing more, the odds go up. Yeah, once they get a bad example, your consistent learner won't output it, right? Because consistent learner only outputs things that do perfectly. Yeah, a lot of definitions kind of all in that statement. Okay, so that's sort of like a PAC learning kind of thing, right? Some kind of so some things are possible. Okay, so if you go to something like disjunctions, just an example of a finite hypothesis class, um, how many disjunctions over n variables are there? Someone say 5? What? Oh, three to why 3?
Because you either take
True, false, or not.
false or
Positive, negative, or not at all?
You have the empty set.
Oh, there's nothing there. Okay. So most 3 to the n. Okay. So this starts saying that once m is at least roughly n log 1 over delta over epsilon, so something proportional to the number of features, number of variables, you can start feeling good about any consistent disjunction. Okay. Okay, good. Okay. So besides this kind of PAC learning, there's another notion of uniform convergence, or let me just define this. Okay, uniform convergence. So for any particular sample, I can, in a hypothesis, I can say, okay, how much is it correct or wrong on that sample, right? So I'll just write error sub s if it's really error over a subset of s, where everything's treated uniformly at random, as opposed to error over true. Okay. So here's the next claim. If m is at least same as before, but now over epsilon squared. Okay. For every hypothesis, the difference between the true error and the sample error is at most epsilon. Okay. So if you do get an algorithm that say is able to minimize the sample error, like a regression algorithm, you're only allowed to output kind of regression type things. Okay. Then your true error won't be so far away. Okay, so there's many other situations where you might be able to minimize the empirical error, but does it give you good error? Okay. All right. So why is m set to this bound?
Let me see.
Okay, so we're going to use additive Chernoff, basically. Okay. So it goes from epsilon to epsilon squared because we're going from just trying to hit the thing, to actually trying to get good additive error. Yeah.
what is error? So I mean, what's the difference between error rate and personalized?
The error of h is the true error if you just kind of infinitely sample from a distribution. Error of s is for the particular sample.
Yeah.
Sorry, so S is our sample of m points. So S is drawn from the distribution, but then the error is that it treats all the questions equally. Right? Like I'm going to draw random questions from our various chapters, but then they'll all be weighted equally on the exam. Yeah.
I also would be why we're doing this like uniform weighting instead of like non-uniform weighting. Because like the probability, we could we just have a binary like 0, like if that 1 like it.
So the probabilities of the underlying distribution are feeding into whether it appears in S. Yeah. I mean, it's just like for exam, it doesn't make sense for me to like make the question that comes from the chapter with more exercises worth more because I had a higher chance of getting randomly sampled or something. Right? Okay. Not to keep bringing up a Reddit subject, but you guys are all PAC learning as we go along. Yeah.
I think there has been treated uniformly that we can because we don't know about
Well, I think this is the most common sense thing to do. Right? If you're trying to poll for president, you try to poll the distribution of the population who's going to win president, and then you treat everyone equal. Right? Yeah. I think this is quite intuitive. Okay, so All right, so it's just going to be additive turn-off kind of thing. Oh, was it not written down? It's not even worth it. Okay. So for a particular, yeah, is it really not? Okay. So for fix X, right? For fix H, you have all these samples, and we can make indicator variables, right? We can do 1 if H of on the ice sample is actually not equal to, if it makes a mistake, and 0 if it gets it right. Okay. And now when you start looking at 1 over m of summing over the xi's, this starts to equal the error of the sample. Okay. And then meanwhile, the expected value of this thing, which is the expected thing, is the true error. Okay. And now you're just plugging into this thing here. All right. Yeah, so xi is equal to 1 if it's a mistake, 0 if it's not. So if I draw a random thing and I make a mistake, that happens with exactly the true, right? Because S was drawn according to the distribution. This is another justification for why arrow sub S makes sense, right? You want the expected value of this to be equal to this. Okay. Good. Okay. So what does that mean? That means that if you have an algorithm that's good at minimizing the empirical error over a finite hypothesis class, that'll give you a PAC learner. Okay, because you have some data, you need some, yeah.
So there is a with random variable. You can go like this kind of things.
Well, yeah, so the sample error is, you sampled a bunch of random data and then for a particular hypothesis. This is for a fixed H, right? You sample some data and you see how many mistakes it makes. It's totally random, but each individual instance is independent. Okay, so that's why we can start applying Chernoff. Okay, and that thing is set so that not only is this going to, the probability of deviating small, but it's going to be small enough that you can take the union bound, just like before. Too lazy to write it again. Okay. So all this PAC learning stuff is just like standard Chernoff bounds and stuff. Yeah. It's nothing profound. Well, I mean, it's not like mathematically too complex. Okay. So that's for finite dimensions, finite hypothesis class. Now, so we're going to keep kind of refining on the hypothesis part. So this is something they like to bring up in learning theory classes. At some level, you kind of want the hypothesis class to be small from a general principle of Occam's razor, which I guess has been restated in a million different ways. Aristotle, shortest way possible. William Occam, polarity is never to be posited. I found one by Isaac Newton, didn't give a very long one. Bertrand Russell gave a very Bertrand Russell-y one. The Albert Einstein one you've probably heard of. Simple as possible, but not simpler. Feynman, truth always turns out to be simpler than you thought. Big Aristotle, if you don't stick to simplicity, you'll die a horrible death. Anyone know who the big Aristotle is? Yeah. Yeah, Shaquille O'Neal. So I think this is like after some game where like Kobe Bryant was like hogging a ball, and Shaq is like 7'3", 400 pounds. He's just like, give me the freaking, I'm gonna dunk it on them. Yeah. Anyway, Shaq gave himself many nicknames. It's like amazing how many nicknames he has. But he's the big Aristotle. Okay. Is there a smaller? I think the original Aristotle was probably not so big. There wasn't like great nutrition back then. He was probably also a very young Aristotle before he. Okay. All right. Okay. So I guess this Occam's razor principle. Suppose this is sort of abstract, but suppose like every hypothesis you could choose from can be encoded in B bits. Then how many samples do we kind of need to start getting the same bounds from before, right? So suppose I'm doing a hypothesis class where any hypothesis can be encoded in B bits. How big does M need to be so that all consistent hypotheses, these are just like the statements from before, but now instead of looking at finite hypothesis class, we're looking at some kind of complexity of hypothesis class measured by number of bits. Negative what?
Or D times R1 over W.
Okay, just one sec. There is no D. There is a B. Okay. Yes. Okay. So basically, the punchline is very simple. If everything needs 2 bits, I mean B bits, then the number of hypotheses is at most 2 to the B. And you start plugging that in, and you need something proportional to the number of bits to start getting the same guarantee as before. Yeah, not that deep, but some people are excited. Okay. All right. Okay, now let's do something a little more sophisticated. Okay, so let's look at generalization bounds like this, bringing into bringing into account things like growth. Okay? So this is certainly useful for things like our rectangles and circles and stuff, right? Like for example, the perceptron algorithm always outputs a hyper half space, right? It might be in high dimensions, but it's a half space. You can do the kernel trick first, and now you're in some high dimensions. But the perceptron algorithm always outputs some line, and everything on one side is one color, everything on the other is the other, right? So there's a lot of learning algorithms that naturally have only classify using relatively simple geometries. Okay, so in other words, each hypothesis can be associated with some kind of range, right? Like the range of everything that's labeled true. Okay? And then you can start asking yourself, okay, what's the growth rate of something like this? Okay, moving down here, no. Okay, so if the hypotheses, all the true sets, or maybe all the false sets, have small growth, small VC dimension, also we showed last time. Can we get better bounds? Yeah. Huh? Well, you want it. The point of emphasis here was sort of like, how many points do I need to start feeling good about my output, right? And that was say measured in bits, or if it's a finite hypothesis class. But we may be interested in infinite hypothesis classes. Like for example, take disks, right? You're always outputting a disk to be true or something, right? Now, before we point out if there's n points and n cubed is enough, right? But for us now it gets a little bit tricky because the points are from a distribution. There's no like fixed n. You just say, oh, n cubed, right? So right. So we would like to, all I know about my classifier is it always outputs half spaces that have small growth, but there's still infinitely many half spaces because there's infinitely many points that I could kind of choose to define a half space. Okay. All right. So yeah, just like before, for a fixed set of points, remember the growth function is saying, okay, if I have a fixed subset of points Q, how many different subsets does R induce over Q? So then this R and Q thing is, it's really focusing on the subsets of Q induced by the circle. So if 2 circles capture the same points, they are counted as the same circle. Okay, good. That we did last time. And what we showed last time was that, if you have VC dimension D, then to get an epsilon sample, you want to get all the mass, the distribution to correct up to epsilon. You need D over epsilon squared for VC dimension D, or polynomial growth power D. For polynomial growth power D and an epsilon net, you need a D log D over epsilon. Okay, so good. Okay, so I want to get a similar, PAC learning useful kind of theorem. Okay, but for hypothesis classes where those kind of true ranges have bounded growth, polynomial growth. Okay, n to the D. Okay, so who wants to try to guess? The first one, all consistent learners have error at most epsilon. The second one, your empirical error is going to be off by epsilon for all hypotheses. So all circles, all possible disks, so on and so forth. Anyone want to guess? Yeah. Yeah, so here, let's say for any particular family of hypotheses, right, I can look at, so, you know, h minus 1 of 1 will just be what's all the points that label this to be true. Okay, and I could define like a range space, maybe R of H or W, I mean, whatever. It can be the set of all of these, you know, true sets. Okay, so hypothesis, you know, in learning theory is just thinking about labeling things true or false, right? But I can think of like, oh, the set of things being mapped to true is like a shape, right? It's a subset.
It's like the cube.
Sorry?
It's like the cube in the previous time.
Yeah, so you know, so it is quite possible that, you know, before we had H is equal to rectangles. Rectangle hypotheses, right? So there we were only looking at, scroll all the way up, right? Something like this, right? This is where H is the rectangles, okay? And we could also think of all these rectangles as ranges. They're shapes over some, in this case, infinite set of points, distribution of points. So, okay. But that's a very clear map. But in general, any hypothesis class can be reinterpreted as shapes by just looking at, you know, for a particular hypothesis, what's all the points that map to true? So H minus 1 of H, that's some subset of the distribution, support of the distribution. And so whatever your family of hypothesis, you can ask, you know, what is the growth rate of that, you know, the corresponding shapes? Okay. And if the growth rate is small, then you're okay. Okay, good. Okay, so if your hypothesis has, you know, limited growth, if you kind of reinterpret the hypotheses as shapes, then what do we need, you know, for the first kind of bound, and what do we need for the second? Anyone want to guess? All right, well, I'm going to guess for you, and there's the time. So it's going to look a lot like the epsilon and epsilon sample theorems. That G of 2m thing, that's also means that if G of n is equal to n to the d, then this could just be d or something.
So the two boundaries.
Yeah, so it should really just be our epsilon sample and epsilon net type theorems. Okay.
There's no epsilon.
Oh, yeah, you're right. There should be a square here. Okay. All right. So somehow we need to connect this to our epsilon net and epsilon's whatever theorems. All right, but you can see the appeal, right? Because from a learning theory point of view, you know, the G of 2m becomes like a D or something. But it's saying that you know, to learn, obviously the word learn is doing a lot of work in our imaginations. But to learn, you need a number of data samples that depends only on the complexity of sort of your classifier. If your classifier is only outputting hyperplanes, you need something, you know, just some function of the dimensions the hyperplane is living in, right? And so this idea that you get this kind of miraculous, you can see why people get excited and might want to call it learning. Okay? And all our natural algorithms, because they're simple algorithms, do tend to output simple hypotheses. Okay, doesn't mean you can find a good hyperplane, but it just says if you find a good hyperplane, it's good in truth. If you find a hyperplane that's good for your sample, it's good for the whole distribution with some good probability. This is very exciting. Okay, any ideas? Yeah.
Since like m is greater than the function of m.
Yeah, so that's the same nonsense with the epsilon net epsilon sample, because that was directly what we proved. But this map to just like if it was VC dimension D, that just like becomes a D or something. Yeah. Okay, but it's really saying that you're getting some bound that's equal to the epsilon net epsilon sample. We're going to try to figure out how to basically apply that. Okay, good. All right, so we basically want to apply the epsilon net epsilon sample theorem. So basically the question is, what are the points and what are the ranges? So maybe there's one kind of subtlety to deal with here, is that the natural thing is like the support of the points that the input lives in, right? But and the ranges would just be the shapes of the true sets. But what we're going to do is a little bit different. So I'm going to do x times 0, 1. So the domain that the examples live in and their label or potential labels. Okay, so it's all these kind of xy tuples. X itself may be multidimensional, but okay. And our ranges, okay. So for every hypothesis, oh, I missed the parentheses. I can look at this shape, which consists of all input points and its label that the hypothesis assigns. All input points and its label. So at some level, it's like half of the of our point space, so to speak. Our point space is all of x times 0, 1. And for every point x, it's giving 0 or 1. So if x was finite, then this would be half the space. Yeah. But and we'll also include all the complementary hypotheses, their induced ranges. Okay. Now, you may want to apply the epsilon net epsilon theorem to PR. Well, okay, let me go a little bit more. So now we need a measure to start doing our epsilon net epsilon theorem, right? So the natural thing is if I draw x and y for a distribution, this really means that there's a fixed concept. So I draw x for a distribution and y is labeled by the unknown concept. Okay, so it's kind of folded into a distribution. Okay, what are the odds that this xy is in kind of our lifted range, this x by y range? Okay, which has a semantic interpretation. How can I interpret this? Probably the xy is in RH. Oh, did I get this backwards? Let me make a critical adjustment. I put 1 minus there. I know that kind of seems important. I'm going to flip it. That's all. Yeah. That's the average error. It's going to be exactly the true error of RH. Okay. So we've set it up so that the measure of our range space is exactly the error. And now if we look at our original bounds, right? I want to make sure that anything with high true error gets hit. That means anything with high measure gets hit. This is exactly what we want from an epsilon net theorem. There's only one catch. Why can I not directly apply the epsilon net theorem? We don't know the G because it's in this lifted space. We know the G's for the underlying hypothesis if I just look at true classes, but we had this 0, 1 thing. So we have to do a little bit of work here, just a little. Okay, so the claim is that if I look at the growth rate of the lifted one, it's going to be at most the original one squared. Okay, so a polynomial goes to a polynomial, D goes to 2D, and then you'll be happy. So if this is true, then everything else follows from the epsilon net epsilon sample theorem. So how do you do this? Okay, so you draw some endpoints and you want to know how many subsets you induce, right? So what we do is we look at, okay, what are all the xi's that got in our sample that got labeled true? What are all the xi's that got labeled false? I got that backwards. Okay, and this would be like the, okay, so S0 and S1 without the primes partition S into two parts. Okay. How many if there were endpoints, then this is what you're worried about. Okay. These just need to be equal. G of M. Okay. Okay. So now, how do I bound this? The number of ranges in our lifted space intersected with S0. Okay, so if I think of H itself as a range space over just X, so this is the family of all true things, kind of an underlying range space. Okay, so S0 is everything that's getting multiplied by 0. Okay, so this is going to be something like, and if I think of H bar as all the complementary, maybe I'll write like 0. Okay, all the things that map to 0. Okay, this will be H bar and S0 prime. Okay, and it's not hard to show that H bar has the same growth rate as H bar. Okay, so you're going to get at most G of size of S0. Okay, this is at most G of size of S. So these are all the it's here. So all the xi's that got labeled 0, all the xi's that got labeled 1. Okay. So this is as a subset of our input space, right? So this hypothesis class is kind of living in X space, right? But this thing is living in X by 0, 1 space, right? So we're just trying to relate the two. We're almost done. I know we're over. Okay. The other one is going to follow this should have been absolute or size of. Similarly, okay, something like this, G of S1, which at most G of S. So I can kind of handle them separately, these two kind of what gets labeled true and what gets labeled false, because now I can remove that last label and go down to a small space where I have a normal growth rate. Okay, so that's fine. Now, the last question for us is how to bound this. And you can bound it using the previous two, but how? Once we get this, we're just done. So this again is how many subsets in the XY space are induced by our hypothesis class. Right? So you have some subset of S, which has things that are labeled true and some things that are labeled false. Right? Okay, so some member of here is some subset of this XY space. Some points that are labeled true and some points that are labeled false. Right? And so some level, well, how about this? So it has some subset that's labeled true. So that'll be R, H, and S1. And it has some subset that's labeled false, R, H, and S0. And then you multiply it together because it's one subset from each. Yeah? And so that's how you get G of size of S squared. Okay? So when you do this lifted thing, which is what you need to really apply the epsilon net epsilon sample theorem correctly to these labeled examples, then you have to do this trick to kind of multiply them together. Okay, but once you get it bounded and squaring is not that big a deal, polynomial stays a polynomial. Then now everything, the original theorem is just an expression of the epsilon net epsilon sample theorem that we did last class. Okay, so you just needed this one trick to deal with the 0, 1. Okay, so that's it. That's learning theory in a nutshell. All right, thank you.